far as I can tell. Okay, so our next speaker is one of our illustrious organizers, Johan. I think that, sorry, I'm to check the schedule. Yes, Johan, you're up. Yes, so Johan will tell us about groups, rings, and fields.
Thanks a lot. Okay, can everyone see the screen now?
Yes.
Nice ASCII graphics.
So fancy.
Yeah. Okay, groups, rings, and fields. So the usual reminder on updating the exercises. So as others have done, I'm presenting straight from the exercise sheet. And we've actually added the instructions on the homepage of the workshop. So you can find them there on how to update your copy of the exercises. Okay, so I'll be talking a bit about the algebraic hierarchy and what we have in MathLib. And of course, there's way too much to cover in detail in 10 minutes, but Patrick has made a wonderful website. And unfortunately, I think I cannot, like I shared only VS Code, so I cannot click on the link and show you what it looks like in the browser, but you can take a look yourself at some point. So we have all the basic concepts, groups, rings, fields, modules, etc. And then, of course, the integers are an ordered ring, and the ordering and the addition and multiplication are compatible in the expected way. So we have structures to talk about that, because then you can prove things for the integers, but you prove them at the same time for the real numbers, which are also an ordered ring. We have type classes that express that a group structure is compatible with a topology and things like that. And then, of course, there are all sorts of constructions that we're interested in. So polynomials, multivariate polynomials with variables indexed by some type sigma. Monoid and group algebras. We have the p-adic numbers, p-adic integers, z modulo nz, localizations, and lots more. Lots of interesting theorems. And I think one of the easiest ways to get a sense for what is there is to just look at this overview website. So what I want to explain in the next couple of minutes before launching into the exercises is how to actually get a sort of grip and feel at home in the library. And the most important thing for that is to know globally where things are, and then to know how to search for things in detail. But before I go explain that, let me say a short word about morphisms. And Kevin also already said this about subgroups. Like, subgroups used to be unbundled, and now we're in the middle of a phase where we are transitioning to bundled subgroups, and a similar thing is happening with morphisms. So at the moment in MathLib, we have the following notation. So x, right arrow, y is just an ordinary function. We've seen them a lot. And then if you add the plus sign to the arrow, then it becomes a morphism of additive groups or additive monoids. So it has to respect 0 and plus. And similarly, you can have like multiplicative morphisms and ring morphisms, etc. And so the difference, what you sometimes see in the library still, is that we write things like this. So we have a function from R to S, and then this type class assumption that it is a ring homomorphism. But the new way to write things is like this. And there are some subtleties why one seems to work better than the other. It has, for example, to do with the simplifier. So this is just a warning that, I mean, it's a library that is heavily under development, and some things are in a state of flux.
What does trivial mean?
Trivial is a proof of true. So true is a proposition, and you can, this part of the line is not really important. It was just that I wanted to write some lean code that explains how things are done.
Or you could write variables instead of examples.
Yeah, that's true. Okay, anyway. And okay, so one thing to say, like in the old way, f was an actual function. In the new way, f is a term of this type called Ringhom. Here you can see it. It's called Ringhom, and we use this for semi-ring homomorphisms and ring homomorphisms. And this heavily relies on the coercion to function that we have already seen before this week. So if you write something like, let's say we have an element R in R, then we could try to write FR. Of course, this now doesn't type check because this is going to be a term of type S, but you see that F just behaves as a function because we've told Lean how to think of terms of this type as functions.
Maybe you can replace true by S.
Yeah, let's do that. Okay, now it type checks. Great. Okay, so where are these things in the library? And things are scattered a bit in 5 different directories. So there's algebra, and it took me a while to understand what was meant by these directory names. So algebra doesn't mean everything that a mathematician would call algebra. It's actually more meant for the sort of basic definitions and properties. And that sounds a little belittling for the word algebra, but it got its name from this algebraic hierarchy. So if you think about all the algebraic concepts you know, groups, rings, fields, etc., and you put them in a big graph, every field is a ring, every ring has an underlying additive group structure, etc., etc. This whole graph, all the definitions that belong to this graph, they are in this directory. But then also some other stuff got added, so it's no longer really as simple as that, but this is roughly speaking for basic definitions and properties. And then all the advanced or specialized material goes in specialized subdirectories, group theory, ring theory, field theory, etc. And finally, there's the data directory, and this is where definitions of concrete examples are. So to give an example, all the basic properties of ordered rings will be in the algebra subdirectory, but Noetherian rings are sort of specialized, so they're in ring theory, and the Chevalley-Warning theorem will be in field theory. But the definition, well, not the definition of natural numbers, because that's so basic that it's done in Lean Core, but lots of basic lemmas about natural numbers are in data. The definition of the real numbers, the definition of the p-adic numbers are also in data. And this is maybe not the optimal way of organizing things from the point of view of a mathematician, but it's sort of standardized now, and this is the way it works. So if you know it, then I guess that already takes away half of the problems. And then how do you actually find things if you're looking for particular things? Well, we've already seen library search quite often this week. And it often helps to carve out the exact statement of a lemma that you're looking for. Then library search works best. There's the online documentation. Again, I would have liked to be able to open this, but I couldn't find how to share my entire screen. I just only shared one window in Zoom. Anyway, so you can also look there, and there is a search bar that just uses Google search, but people are working on a new search bar that like really understands Lean source code and can offer more advanced search capabilities. I often use the old school Unix or Linux tool grep to just search through the files. And then you can search in VS Code. So if you hit Ctrl-Shift-F, let me do that. Then, for example, okay, one thing to be aware of is that by default by default it looks like this, and you don't find anything. So you have to click these 3 little dots and then click this blue cogwheel, and then it will not search only in the current file, but it will search through the entire library. And then you can find things like the Hilbert basis theorem. Another way to search in VS Code is if If you hit Control P, then you get this drop-down menu, and you can search for file names. So, for example, I can search for topology, and we'll find other files in this particular project. So if you're working on Mathlib itself, that's a very useful way to find files in Mathlib. I can also search through all the lemmas and definitions that have been imported so far, and then I hit Control P and I type this hashtag symbol, and then I can, for example, search for polynomial dot, and then I'm guessing I want to show that polynomial rings are Noetherian, maybe, and then here I see that polynomial is Noetherian ring, and this is then the Hilbert basis theorem. Okay, so that's lots of search tools. Another very powerful thing is the autocomplete. So Mathlib follows a very strict naming convention. The binomial theorem is not called binomial theorem, but add pow, because it is about adding two things and then taking a power. And after a while, you get the hang of this, and you can just start guessing names. And I guess, especially because Euler proved so many things, if we just call everything Euler's lemma or Euler's theorem, it becomes confusing, and you would need lots of namespaces to distinguish. So sort of inferring the name from the thing you're proving sort of gives everything a canonical name. And to demonstrate this autocomplete, because then you can start guessing the name and Lean will give suggestions. So here we're trying to prove something silly, 57 plus the sum, where I look at the set of 0 up to n plus 1 minus 1, so 0 up to n is of course the same as 57 plus f of n, and then the sum of all fi for I in 0 up to n minus 1. So to prove that, my guess is, okay, we're talking about the sum over a range, and then here I get all these lemmas, and I say, oh, well, actually this looks really, really helpful because it was the range of the successor of something. So let me do that. And voila, it worked. It was exactly what I wanted. And then you can see here in the goal that the only thing that distinguishes the left and the right-hand side is some parentheses. So if I now rewrite by associativity of addition, then we've proven this thing. So sort of understanding the naming convention, once you've done that, that's a really powerful way of finding things in the library. And finally, another strategy is to, if you want to prove something about X, just jump to the definition of X and look through the next 3 screens about for useful lemmas about it. For example, I can jump to the definition of the coefficient of a polynomial, and then I quickly find, oh well, stupid things about the coefficient of 0, teaching it to the simplifier.
Excuse me, what did you do to do the jump?
Oh, sorry.
You must have pressed some key, yeah, but we can't see that.
Right. Okay. So actually, I can right-click and then go to definition. What I did, sorry, this is completely muscle memory, is I did control-click. Control-click also takes you to the definition. So I push control and then I click.
Okay, thanks.
Yeah, good question. And then you can just look through the first few lemmas after that definition, and if you're looking for some basic fact, then it will probably be there. Okay, so I didn't.
Johan, maybe you can also briefly speak about this clicking on the tab you told me yesterday. So
okay, yeah, right. So if you, okay, let me show you another trick, a couple of tricks with VS Code. So, okay, so I jump to this definition. Now here the font of this tab is upright, and here it is italic. So if I now jump to another definition, say polynomial, then it jumps in the same tab, whereas before I jumped out to a new tab. So what I can do is I can double click on the name of the tab. Now it becomes upright. If I then click on definition of semi-ring, you can see that polynomial.lean is still there, and I get a new tab. So if you want to jump to 3 different definitions and look at all 3 of them, this is a useful trick. Okay, so I mean, I didn't explain what a ring is or a field is because I assume everyone knows this. So, and I cannot show everything there is in the library. So I've basically tried to teach you how to discover the library yourself. And then, yeah, I suggest we just launch into the exercises and try to figure out, yeah. I've written some hints at the place of the exercises, and but also I gave you instructions how to sort of discover the library yourself. So look up the definition of finite dimensional and search the library for useful lemmas about these facts. The first 2 exercises are warming up exercises. Exercise 3 will define the Frobenius morphism, and for that, of course, you need this fundamental fact. So that's a sort of challenge, but of course it's already in the library, so you can just use that if you are not interested in this challenge. And then you can see how to define this bundled morphism, Frobenius. And these are all sort of rather easy once you have this fact. And then exercise 4 is pretty challenging. So yeah, I've written some hints. We'll prove that if you have a monic polynomial f and it's irreducible modulo some prime p, then it's also irreducible over the integers. And finally, there's some bonus exercise. If you've solved everything, then you can look at that. So I'll stop here, and then people can start working on the exercises. Thank you.
Yeah, thanks, Johan. Also, thank you for the beautiful ASCII art.